This evening, we're very lucky to have Dr. Sarangi. Riti got her bachelor's degree from St. Xavier's College in Kolkata, and then she came to Stanford to do a PhD in chemistry. While she was here, she learned about the beauties of X-ray science, and she never left. And now she is actually a staff member at SLAC, at the Stanford synchrotron radiation light source, and one of the world's great experts in the organometallic chemistry of biological molecules. Now, I'd love to tell you that Riti has a secret existence as an underwater Cape Crusader, but that wouldn't quite be accurate. But nevertheless, her secret life is pretty interesting, and we're going to hear about it tonight. So, Riti, please tell us how you're going to save the Mary Rose.
Thank you, Michael, for the introduction. Is this working? I guess so. Hello, everyone. Sorry? Oh, perfect. All right. I'm going to tell you a story tonight. This story spans 400 years and follows the life of a 16th century warship called the Mary Rose. We'll go over the glory days of the Mary Rose, its unfortunate sinking and years of oblivion, followed by a chance finding of the ship and the story of the modern-day Mary Rose. So, not much is known about the making of the Mary Rose, but historians know this, that King Henry VIII came to power in 1509. He decided to expand the British Empire into mainland Europe, particularly into France. And to do that, he wanted to expand his naval force. He commissioned 2 ships to be made in 1509, and one of them was going to be the flagship of his naval fleet. And as such, it was going to be heavily decorated and quite expensive. The naming of the ship was after his sister, Mary, and the Tudor emblem, the rose, hence the Mary Rose. Now, the ship was used for 30 years for miscellaneous purposes. In 19th July 1545, the ship was first used as a battleship against a battle against the French Navy. Now, before the ship could even enter into battle, unfortunately, it floundered and sank near Portsmouth Harbor. Historians say that the ship was trying to take a very sharp turn. In the process, it tilted to one side. And accidentally, some of the gun ports on that side had been left open. Water came in, the ship got disbalanced, floundered, and sank. This picture shows you a detailed painting of the actual sinking of the ship. You can see the mast of the ship right here. This is sort of an expanded image. People are all trying to run away from the ship, and this is where it's going down. Of course, the French claim to this day that they sank the ship. Nonetheless, it lay at the bottom of the ocean near Portsmouth Harbor for 4 centuries, all but forgotten. Now, it was rediscovered briefly in 1836 by some local farmers whose line started catching against something metallic underwater. They did some diving, some expedition underwater, but it was soon forgotten. In 1965, the search for the Mary Rose was restarted and spearheaded by a war historian named Alexander McKee. He and his team really wanted to find the Mary Rose and did a lot of studies to pinpoint where it was buried. In 1967, they did some side scan sonar and found that there was some object under the seabed that shouldn't have been there. It was a very large object. And that really got them very excited. They thought it was the Mary Rose. And between 1968 and 1971, a lot of volunteers came together. They started diving around the area where the subsonar activity was, the subsea seabed sonar activity was found. And they started retrieving guns and pieces of timber, etc. In the early 1970s, a large piece of timber was found. And that got everybody excited. The British government got involved, lots of money flowed in, and in 1979, the Mary Rose Trust was established for professional excavation and preservation of the Mary Rose. And I'm going to show you what happened to the ship when it was submerged. This is a video which is showing what happens. It'll show you. Let's see. All right. So the ship sank on its starboard side and very soon filled up with some silt clay. And the bottom side, the starboard side, got trapped, but the top side, the port side, was exposed to the water, and it slowly dissolved and went away. The bottom side, though, was completely preserved because it was under all this silt, and slowly over time, more clay started building over it, and between the 17th and 18th century just got completely submerged under this light clay. All right, let's get back. All right. So the ship sank near Portsmouth. Portsmouth is a southern port city in UK. And you can appreciate that it's strategically placed for an attack on France. And this is where King Henry VIII was amassing his naval fleet to mount his attack. The top right shows you an expanded picture of this area. You can see the harbor. This is the water going inland, and this is where King Henry's fleet would have been docked. Bottom picture here is a modern day representation. The Mary Rose Trust is somewhere out here. All right. Imagine excavating a huge waterlogged ship. The technology has to be perfect, and the method to lift it out has to be very precise. Otherwise, we could damage the ship. So the Mary Rose Trust devised a three-step plan. The first was to attach the ship to a horizontal beam using metallic cables that was attached to bolts that have been placed on the ship at different places. Now, the idea was that this horizontal bar was going to be sucked up using hydraulic devices that would bring it out of the silt and clay. Once it was out of here, it would be gently transferred underwater into a custom-made cradle and left there, like that. And then this cradle would be lifted out using a high-precision crane. This is a picture of the crane that was used. Here you can see the remains of the Mary Rose sitting inside the custom-made cradle. And then it was transported to the Portsmouth Historic Dockyard and housed in the Mary Rose Museum. It's a huge room, and people can look at the ship through glass viewports. All right. Now, before the excavation of the Mary Rose, the idea about the ship, or the picture of the ship, was based on artists' impression, what people had drawn the ship to look like. You know, it was going to be a flagship, so they had drawn it to have several masts, it was heavily decorated, etc. But only after the ship was excavated did historians get a true picture of what the ship was like. And they think the ship looked something like this. It had several different decks, starting from the hold at the very bottom to the orlop, main, upper, and castle level. So the hold is level where the common sailors used to reside. And as you went up, the top brass of the Navy, the admiral would live somewhere here. The ship for those times was actually quite big. It was 45 meters long, or about the size of half a football field. It was 12 meters wide, and about 12 to 14 meters from water level. And based on these dimensions, the weight of the ship is estimated to be between 600 and 750 tons. Now, the ship sank with 400 people on board, out of which only a few survived. And with it went all the everyday things that these 400 people used. And since the ship was buried underwater, it was trapped in time. Nobody could touch any of these artifacts. Nobody had even disturbed them. So they were sort of pristine, and they gave you a very good glimpse into the everyday lives of these sailors who lived in those Tudor times. Some of the artifacts that were discovered were expected. They were utensils that people ate in, or they were shoes. But some were rather unexpected, like elaborate grooming tools. I wouldn't expect sailors to have fancy combs and nail files. But then there were many, many of these combs that were found. And some of the artifacts were rather unique. There was an elaborate carpenter's tool, a cow horn, ink pot, even the remains of a dog, which was used as a rat catcher on the ship. That's why no remains of the rats were found, because he ate all of them. But the most numerous of the artifacts were, of course, and as you can guess, instruments of war, from large cannons to small guns. But you know, we're forgetting one thing. Apart from all the artifacts that were on top of the ship itself was a big artifact. In those days, ships were made exclusively of wood, and so was the Mary Rose. Now, wood is quite an interesting material. Here I'm showing you two images. On the left is the image of wood that's been sketched, and on the right, it's a close-up image of what wood looks like in micrometer range. Now, wood has a structure which looks like this, but you can imagine it as a porous, fibrous network. There are thick rods in it that are made of cellulose. And these thick rods are sort of held together by a material called lignin, and you can see them here. In the real image, you can see the cellulose rod and very thin filaments that are lignin. Now, as the wood rots, most of the other thing just goes away, vanishes away, and what's left is a scaffold of cellulose and lignin. Now, once the ship was brought out, it was important to preserve this scaffold. We didn't want the ship to collapse once it was brought out of the water. So for 8 years, it was sprayed with cool water inside a huge glass room. After that, it was sprayed with something called polyethylene glycol. And polyethylene glycol is a gel-like material, which sort of is a carbohydrate. And it's thought that this peg would penetrate the wood surface and go and form a supporting scaffold for the wood, sort of support the cellulose and lignin structure that's left behind. And when the ship would eventually be dried and brought out to the public, it would hold up. In 2004, they sprayed the ship with a concentrated solution of PEG, hoping to accelerate the process of this strengthening of the scaffold. And that's what they're spraying till now. You can see a little sprayer here. This is where the PEG and water solution is mixed and sprayed on the ship. But in early 2000s, the preservation scientists started seeing a new development. What they observed was on the artifacts that were not being sprayed by wood, for example, a gun port like this, there was some yellow salt deposits that were being formed. And the wood beneath the salt deposit was getting softer, it was getting mushy. And so they were really puzzled. They wanted to know, what's this potentially dangerous salt-like material that's being formed, and why is it causing the wood to degrade? And to answer this question, we had to go to Sweden and to the Swedish warship Vasa. Now, the Swedish warship Vasa sank near Stockholm harbor in its maiden journey. It's rather embarrassing because it only moved about 124 meters and sank. They excavated it. It actually sank in 1628, and they excavated it in 1961, and in a rather pristine-looking condition. This is what the ship looks like. You can see the whole ship. But what's most interesting about this ship is that similar salt-like deposits were observed on the Vasa. Now, preservation scientists started working on this, done a lot of research, and they've come to a theory on how these salt-like deposits are formed, what they are, and how they're destroying the ship. Now, I'm not going to go into details about what's being done on Vasa, but I'm going to tell you in a stepwise fashion what really happened. First, the ship sinks, and it goes to the bottom of the ocean. At the bottom of the ocean, there really isn't any oxygen. And under these anoxic conditions, bacteria that live on sulfur thrive. And what these bacteria do, they produce reduced sulfur species. And what reduced sulfur species is basically sulfur compounds that has no oxygen around it. It has got other elements around it. And so what this bacteria did, started growing these reduced sulfur on the wood surface. And 400 years later, this ship is now concentrated with a lot of these reduced sulfur. Then what we did was go down and salvage the ship, bring it out, and the process expose it to oxygen. And then oxygen reacts with these reduced sulfur species. It forms sulfur-oxygen bonds and forms what's called the oxidized sulfur species. And one of the oxidized sulfur species that's formed was sulfuric acid. And you can imagine what sulfuric acid would do to the wood. It basically degrades the cellulose and lignin. It eats it up. So acid was being formed, which was eating up the cellulose and lignin, and the sulfuric acid also formed something called the sulfate salts, which were deposited at this salt-like material. That's what was going on in Vasa. Here I'm showing you an example of just that. This is a piece of wood, waterlogged wood, that has been severely damaged by sulfuric acid. And on this side, it's also a piece of waterlogged wood which hasn't seen that much degradation. You can see the difference. So what are we saying here, really? The reduced sulfur comes into contact with oxygen, water, forms sulfuric acid, and decays the ship. So should we never really have brought out the ship? And should we really let sleeping ships lie? This is where SLAC comes in, and where I get involved. I'd like to tell you how really I got dragged into this research. To do that, let me show you what I really do. This is the spectrum of light. Some of you might have seen it. It spans over radio waves, which are very low frequency, low frequency, to gamma rays, which are very low frequency. Now, the Mary Rose is about the size, or has the dimensions, of radio waves. It's huge. What I work on, in general, are proteins. They're tiny samples. I study the molecular composition of these proteins. The Mary Rose is 10 orders of magnitude larger than what my world is. But I found motivation from 3 things. The first was Ellie. She was a good friend of mine, still is a good friend of mine. She was at that time was doing a postdoc at University of Kent in Canterbury. and working on the Mary Rose ship. And she wrote to me saying that she'd like to do some sulfur spectroscopy and would like to set up a collaboration. So I agreed to that. The second thing is I got to visit exotic places. Canterbury is really quite beautiful. And the third and rather important one, ancient warships are super cool. Who can say no to them? Right? So I really got hooked. Okay, so what we did was we took 3 centimeter by 3 centimeter samples of the Mary Rose wood. Those were some of the samples. We also had some tiny little cores about half an inch in diameter and about 4 or 5 inches long. These kind of samples that were studied here. So they started in England, near Portsmouth, at the Mary Rose Trust. They were first transferred to Canterbury, and from there sealed and brought over to SSRL. Right? Now at SSRL, which is a subdivision of SLAC, we study matter using 2 techniques. And before I go into exactly what I did, I'd like to explain those 2 techniques in little detail. So the 2 techniques that we use are diffraction and spectroscopy. I think you can all see an image at the background here, which is not too obvious. It's sort of vague. And the question that I want to ask is, what is this image? What are the things that are present in this image? Where are they placed? If I ask this scientifically, I want to know, how are the atoms arranged in this material, right? And so I'm going to use diffraction to look at it. And when I do that, I get this image. I get the positions of everything, and it seems like there are some fruits in bowls. But I don't know which fruit this is. I don't know if this is an apple or an apricot or a peach, right? And diffraction is never going to help me with that. So what I turn to is spectroscopy. Spectroscopy can tell me exactly what this fruit is. Or in other words, it can look at individual atoms and tell me which element they are, right? So we used spectroscopy, and we figured out that one of these was an orange and the other was an apple. If we put these 2 together, we come to Cézanne's apples and oranges. All right, so what we did was use spectroscopy to study the Mary Rose. Let me go into a little bit detail about spectroscopy. Now, spectroscopy is the study of the interaction of light with material. When light shines on any material, it's reflected off and gives a specific spectrum. If you measure the spectrum, you can get a lot of interesting things. All objects in the world have a very specific spectrum. And if we study it, we can know the specific chemical composition of that object. So I'll know that this is a duck, this is the Colosseum, and this is the iPhone, just by looking at the spectrum that's coming out of it. So it's a fingerprint. And that's what we're going to use spectroscopy in the context of Mary Rose. We're going to use it as a fingerprint. All right. Now this is what a typical X-ray spectrum looks like. At the bottom is an energy scale, and on the right is the intensity scale. All right. I'm showing you the spectra of several different iron compounds. One of them is iron oxide. The other is an iron sulfide. One of them could be an iron carbonate. But you can appreciate that there are a lot of differences, and all of them are rather unique. And because I have measured these compounds before, I know when I measure them again in an unknown, I know, aha, this looks like iron sulfide. So this sample must really have iron sulfide. That's the whole way of looking at spectroscopy here. But the one thing that you can also appreciate is there's a similarity in shape. They all sort of go up at around the same energy and sort of go up to the same intensity. This is where sulfur is rather unique. I'm going to show you now the spectrum of several different sulfur compounds. This is what they look like. You can see they're very different in energy and very different in intensity. All right? And so this can be used as a very good fingerprint of the material. If my material has a peak here, I'll know, aha, it's this. If it has a peak here, I'll know it's this. Now, I'd like you to pay attention to this slide because I want to explain the difference between reduced and oxidized sulfur. Remember I told you reduced sulfur compounds were those that didn't have any oxygen bound to them, and oxidized sulfur have a lot of oxygen bound to them. This is the difference in their spectrum. The reduced ones are sort of lower in energy and lower in intensity, and the oxidized ones are higher in energy and more intense. And the most intense and the highest energy one is sulfate. Now let's correlate it with the spectrum of sulfur that's expected on the Mary Rose. Remember I told you that the Mary Rose has reduced sulfur species, which is oxidized when you bring it out in air. So you're going to find some reduced species. You potentially maybe find some oxidized sulfur and a bunch of sulfate salt. Now, sulfate is just a superoxidized form of sulfur. Now I'm going to make a theoretical construct of what I expect the Mary Rose spectrum to look like. I have no clue. I want to just make it based on what I think it should look like, all right? And this theoretical construction is based on some of the research that had been done on this ship, Vasa. So in normal wood, before the Mary Rose sinks, the total amount of sulfur is very low. There is some reduced sulfur, it's part of the ship, the wood, and some oxidized sulfur, which is also part of the wood. I'm going to draw two bars, one in blue and one in red. The blue bar to lower energy represents reduced sulfur. The higher bar represents oxidized sulfur, all right? Now the ship sinks and goes to the bottom of the ocean. Bacteria starts to act on it, and reduced sulfur is increased, right? Will look something like that. Okay, we're going to bring the ship out of the water. Some of this reduced sulfur is getting oxidized, gets converted to oxidized sulfur. So reduced goes down a little bit, oxidized goes up, and the total amount of sulfur increases because obviously the bacteria have put on a lot of it in here. So what I'm going to do now is create my spectrum for the Mary Rose by adding the data for the reduced and the oxidized sulfur together. And this is what I think it should look like. All right? As I said, this is what I would expect theoretically. Now what we did was we took two different samples from the Mary Rose and measured the sulfur spectroscopy on it. And this is what you see, all right? They are very, very similar to what you'd be constructed from theory. One thing you'd also notice is even though they're quite similar, there are small differences. That's because the Mary Rose is a complex wood structure. Some of the places were shielded from the bacteria, some got more action, some of it just weathered away. And so it's expected that there will be some variability. Now we want to understand what are the sulfur species that are present in the Mary Rose wood. Now, as I said, since it's so complex, we don't want to know every little sulfur compound in it. We want to know what are the major components in the wood. And to do that, we have something called the fingerprinting technique, where we take known compounds, the data from known compounds, and sort of match it against the data from the Mary Rose and try to see if they fit. Here I show you the Mary Rose data in black and 4 different compounds that were necessary to fit the Mary Rose data. And And we get a reasonably good match between a combination of these four different compounds and the Mary Rose. So the combination is in the dashed line. And the four compounds are pyrite, which is a reduced sulfur. It's an iron sulfide. Cysteine and cysteine, they're components of wood, and they're also produced by bacteria, and they're sort of expected in the wood. And nitrogeroside, an iron sulfate. Now you're going to say, hey, Riti, stop. Iron sulfide, iron sulfate, where's all this iron coming from? The Mary Rose ship was built with wood, but it has a bunch of nuts and bolts and lots of different iron material on it. As the ship sits at the bottom of the ocean, the iron starts to rust, it starts to dissolve, and then combine with the sulfur, forming all these compounds. So in hindsight, it's sort of expected, really. All right. So what we observe is the exact thing that happened to Vasa is happening to the Mary Rose. Some sort of an oxidized sulfur compound is being formed, acid is being generated, and that's what's degrading the ship. That's what's forming all these salts. So should we really have left the Mary Rose buried? Or can we do something about it? And this is where Ellen Chadwick, her advisor at that time, and us here at SSRL devised a method for the neutralization of the acid and treating of the sulfur problem. And we looked into the literature of archaeological artifacts, and we decided to try one compound that had been previously tried in a different field of archaeology, never with wood, and see if that worked. And the reagent that we chose was strontium carbonate. We wanted to grind it into very tiny particles called nanoparticles, really dust-like particles, and use that on the ship. Now, very tiny particles because they can penetrate the wood. They're also soluble in water, so we decided we could dissolve it in water and spray on the ship. Now, strontium carbonate has few very specific properties. It has strontium. Sorry. All right. It has strontium, which forms an insoluble sulfate. And the idea is that it'll go in, all these sulfate salts that are present on the wood is going to suck it out, form an insoluble compound, and that we can just wash off with water. And it also has carbonate. Now, carbonate is going to convert the sulfuric acid, which is rather a strong acid, into carbonic acid, which is a weak acid. Also, the carbonic acid is effervescent, so it can form carbon dioxide and water, and maybe it'll just leave the wood, right? And so we wanted to try this on the wood. And to do that, we wanted to answer three questions. First is, does the strontium carbonate really penetrate the wood? Second, does it react with the sulfur and third, does it form sulfate salts? So let's address the first question. Does strontium carbonate penetrate the wood? This is a scanning electron microscope image of the wood, basically a very close close-up of the wood surface. This is about 10 microns, and you can see sort of the network that I was talking about of cellulose and lignin. When you treat this wood with strontium carbonate and look at the strontium spectrum, this is what you get. And I'm hoping you can appreciate that there are light green patches all over the place where all around these networks, these grooves. And that shows the presence of strontium. The strontium has really penetrated the wood and gone all the way in. So we are successful there. But does the strontium carbonate react? And to do that, what we did was take a piece of wood from the Mary Rose, measure the data from it, and then treat it with strontium carbonate and measure it again. So this is the data before treatment with strontium carbonate. And as I said, you have some reduced and some oxidized, sulfur in it. Okay, when you treat this with strontium carbonate, this is what you get. You see that the reduced sulfur has sort of gone down in intensity, and the oxidized one has grown. So strontium carbonate really does do the chemistry. But the third question is, this sulfate that's formed, is that strontium sulfate, or is it just some other sulfate? We know that the big peak grows in there, but how do we know strontium is attached to it? And to learn that, we have to look at a different region of the data to a little bit higher energy. All right. Here I'm showing you the data from 4 different kinds of sulfates: strontium, iron, calcium, and sodium. You can see all of them have this big peak to low energy, and they're sort of all similar looking, right? But to higher energy, you can see that they have a characteristic fingerprint depending on which element I'm talking about. So what we are going to do, we're going to use that part of the spectrum to determine whether it's strontium sulfate or some other sulfate. Okay? Here I'm showing you a comparison of the iron sulfate that we used to simulate the data before treatment with strontium carbonate. This is the Mary Rose, this is the iron sulfate, and you can see the signature of the iron sulfate in the Mary Rose data. All right? This is after treatment. I'm sure you'll appreciate that the 3 features that are present in the Mary Rose are from strontium sulfate. So this clearly shows that all of this sulfate has been converted to strontium sulfate. Strontium has gone in, sucked out all the sulfate and formed an insoluble compound. So this is pretty strong evidence for that. So we have 3-fold results. We show that yes, strontium carbonate does migrate into the Mary Rose, that it does react and form stable strontium sulfate, and in the process does oxidize reduced sulfur forming strontium sulfate. So is the solution just spraying the ship with a mixture of the PEG and strontium carbonate thrown in? It's not really that easy. The first reason is that we have studied these tiny little pieces of Mary Rose wood. How do you scale it to this huge ship? There are cost factors. Is this the cheapest thing that we can find that will treat? I mean, imagine having to spray this huge ship with strontium carbonate continuously for years. It's going to build up. The expense is going to build up. And so there are several different things that we still need to address about it. But the good news is Ellie is now in the Mary Rose Trust. She's now employed there as a preservation scientist, and we've recently started setting up another collaboration where we can look at it in detail to really take the study from the lab and apply it to the Mary Rose. The work that we have done here and that we continue to do here to preserve the Mary Rose itself and the thousands of artifacts really gives us a very close look at the Tudor times. Not only us, it's going to stay on for future generations if our preservation technique really works. Now, I want to leave you with a thought. Mary Rose today doesn't look like this. It looks more like this. We can't restore it to its glory days. But I hope that the work that we have done here and that we continue to do is going to help other historical artifacts from not getting damaged. And really, the sulfur problem, for the formation of sulfuric acid, etc., is present in many other historical artifacts. Old paintings made on canvas and wood, old silks, vulcanized rubber, paper, old manuscripts, all of them suffer from this problem. And we hope that our work has gone a step towards it. With that, I come to the conclusion of my story. It's been an exciting journey for me. We have gone outside of the tiny world of protein molecules, huge ship. Together, we've gone back 400 years into the past and gone to the bottom of the sea. We've also visited exotic places. And really, most importantly, we've been able to help the preservation of a 16th century warship. And none of this would really have been possible without the support from several different organizations. First is the British National Heritage Lottery Fund, which really funded all the work on the Mary Rose that was being done at the Mary Rose Trust. National Institutes of Health and Department of Energy, which fund me and SLAC here. And I also like to thank several people. Ellie Schofield, who really spearheaded the work at that end in the UK. Apurva Mehta, who was a spectroscopy collaborator here, who really brought a lot of this project together. Mark Jones and others at the Mary Rose Trust. Some summer interns, and Sam Webb for the spectroscopy group. And with that, thank you for your attention.
Thank you very, very much. And we're happy to take some questions. So please raise your hand. Wait until the microphone comes. So.
You explained where the iron came from. Where does the sulfur come from?
So it actually, that's a good question. And I think everybody really asked me that, where's all the sulfur coming from? So there's a lot of sulfur in biomaterial underwater. And the bacteria, they really get it from there and start living on the wood and putting it into the wood structure.
So for example, the cysteine, that's an amino acid.
Right.
It's in everything.
Right, yeah.
The bacteria grab it up.
Yeah, that's what they do. And they actually put the cysteine in, either they put the cysteine in or they convert some other molecules into cysteine and then they oxidize it. They do a lot of other chemistry.
What does a pound of strontium carbonate cost?
Well, we bought it from Sigma Aldrich in grams, and I think it cost about $10 to $20 for a 50-gram bottle. So it was rather expensive. But you know, you don't have to throw in a lot of strontium carbonate. So we actually tested the wood with a dilute strontium carbonate solution, and after less than a week of testing, the acidity of the wood had decreased significantly. So we think that even a small addition of strontium carbonate could help with the acid formation.
Hi. So I visited the Vasa a couple years ago, and they are not currently spraying it with anything, no PEG, at least that I'm aware of. So I'm curious, and maybe you don't know this, has the PEG worked for them, and are they having, you said they're having the same problems, but are they going to have to maybe revert to a strontium treatment at some point as well, or do you know anything about that?
So Vasa, you know, it's a very unique ship. It's excavated. I mean, it was underwater for 300 years, but it's quite pristine. But they have really started seeing the salt-like buildup even on the Vasa ship. As I said, I mean, this is taking the research that we do in the lab to the actual ship is a big process, a big leap. But I think Ellie and the preservation of the Mary Rose, they talk to the Vasa regularly, and I think some of this knowledge is being transferred. I don't know if they will use it in practice or not, but certainly they're considering an alternative treatment. And I'm pretty sure that they will need to do it.
I think you already answered my question, was whether there are some immediate prospects for trying this out on perhaps some very, very small sunken ships or rowboats or canoes or whatever. Okay.
Well, not really. We really haven't tried it on ships. Well, we have tried, as I said, on some vulcanized rubber samples, which are also artifacts. from the early 1900s and things like that.
I was wondering whether you had to take into account the type of wood you were working with and whether, I presume most of the ship was oak, because I think that was what they used, but whether different types of wood would react differently.
So there are two parts to that question. One is whether different types of wood would react differently, and the second, sub-ocean environment is different in different places, right? If the ship sank in the Mediterranean Sea versus the English Channel, it could be different. But in general, we have looked at the data from VASA, and I mentioned the Mediterranean Sea because we also looked at a sunken war ram from a Roman ship that sunk in the Mediterranean. And there is a lot of variability. There's a lot of variability in how much reduced and how much oxidized sulfur there is, but the trend is the same that's observed. So to understand that, in a global perspective, it's a big challenge, but we've really started to look at different kinds of wood now, started looking at what fresh wood looks like, pine versus oak, things like that. We are actually looking at that right now.
Where is the Mary Rose now?
Oh, it's in the Portsmouth harbor. The Mary Rose Trust is located there, and that's where it's housed.
That's very loud. I was wondering how long you would need to spray it with the strontium for it to have a lasting effect.
I'm not sure. I can't really answer that question. But as I said, that on a smaller piece of wood, we did that experiment. And in less than a week, we could see the acid level go down. But can we transfer this information to the ship? If we spray the ship for a week, will it become less acidic? I'm not really sure. There are more factors than just that.
In terms of scaling up, I know you haven't done much looking at that, but has anybody thought about just the total quantities of material that are required, not just the cost, but the products of reaction and the environmental effects of having all this stuff sloshing around that you have to get rid of?
So I really don't think they have looked at that. I mean, the current thought is how to preserve this ancient ship, which is sort of a pride for them. One thing that they do right now is they don't let what's coming off really go away. So they're spraying it with PEG, but they recollect it and respray it, so they don't have to use a lot of PEG, and they recycle it. So that's to reduce the impact.
Oh, how much sulfur are we talking about? Are we talking about part per million by mass or volume or dollars or color or what? I mean, are we talking about 100 pounds of sulfur or a kiloton or do you have any idea?
I know the numbers better with the VASA. The VASA has over a ton of VASA in it. And the Mary Rose, though, the Mary Rose, the sulfur amounts have been a little diverse from different parts of the wood, so estimating it is a little difficult. But still, yeah, it's a lot of sulfur if we go by the study on the VASA.
One more question, and I'd like to ask you a question too. But anyone else? Please. Oh, wait for the mic, please.
I think you may have mentioned it, but could you please repeat it if you did? And that is, why strontium carbonate? Why not some other carbonate? Did you try others or what?
Well, I think we're also going to try calcium carbonate, which is slightly cheaper. Calcium sulfate. Sulfate is also rather insoluble. We basically lifted it out of preservation science and something else. It had worked somewhere else, and we wanted to try it here. But as I said, calcium would be cheaper, and I think it's going to work. That's something we're going to try next.
So what are you doing now to keep it stable while you try and figure out what to do?
Well, we are doing the same as we were. We are spraying it with water and PEG and not allowing anybody near it. It's not for public display yet. In that sense, you can look at it through a glass wall, but you can't get closer to it. And but the thought is that only that is not going to work. We need to add something to really take care of the acid problem, and we really aren't treating that yet.
Okay. And I've got a question I'm just dying to ask you.
Okay.
Did they let you take one of these wooden triptych panels from the Middle Ages and put that in the SSRL beam?
Not the whole panel, but here I have an example of some of the wood from the Mary Rose that we measured. This is the typical size of the wood. If you want to look at them, you can come after we are done. Take a look at some good wood and some damaged wood if you want. Yeah.
Well, let's thank you.